According to the National Electrical Code, or NEC, multiple service entrances can be grounded to a common grounding electrode system. However, each service entrance must be individually connected to the grounding electrode system. The method used by the contractor is acceptable as a common grounding system under the following conditions. Firstly, the bare 3/0 ground wire is continuous and unbroken. Secondly, each panel is connected to the ground wire by a lug bolted to the enclosure. Thirdly, the lug is properly sized for the wire used, which is 3/0. Fourthly, the ground wire is connected to the building steel and slab rebar, providing a path to ground. The NEC does not specify a minimum size for a ground rod. However, a 3/4 inch diameter copper-clad steel ground rod is commonly used and should be sufficient for most applications. The bare neutral jumper should be sized according to the overcurrent protection device, or OCT, serving the panel. In this case, the jumper should be sized for an 800 amp OCT, which would require a conductor size of 2/0 copper. Oversizing the common ground is not required by the NEC. However, it can provide additional protection in certain cases, such as high fault current or frequent lightning strikes. The common grounding method used by the contractor is acceptable provided that the above conditions are met. An additional ground rod or water pipe grounding is not required in this case. Now let's delve deeper into the specifics. When dealing with multiple service entrances and their grounding requirements, the NEC provides guidelines to ensure safety and proper functioning of the electrical system. The core principle is that while a common grounding electrode system can be used, each service entrance must have its individual connection to the system. This ensures that each service has a direct and reliable path to ground. Now let's talk about the grounding conductor. The contractor used a continuous and unbroken 3/0 bare ground wire. This is a key aspect of the installation. The continuity of the grounding conductor is crucial because it maintains a low impedance path for fault currents to return to the source, which facilitates the operation of overcurrent protection devices like circuit breakers or fuses. If the conductor were to be broken or have higher resistance connections, it could impede the flow of fault current, delaying the activation of these protective devices and increasing the risk of electrical shock or fire. The NEC specifies requirements for the size and type of grounding conductors based on the size of the service entrance conductors and the overcurrent protection devices. The 3/0 size is likely appropriate for the 800 amp service panels, but it's essential to verify this against the NEC tables, specifically Table 250.102, which dictates the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. The method of connecting the grounding conductor to each panel is also important. The contractor used a lug bolted to the enclosure of each panel. This is an acceptable practice, provided that the lug is listed for grounding and is properly sized for the 3/0 conductor. The connection must be mechanically sound and provide a reliable electrical connection. The lug should be made of a material compatible with both the enclosure and the grounding conductor to prevent corrosion, which can increase resistance and compromise the grounding system's effectiveness. The NEC section 250.8 covers the requirements for making effective grounding connections. The grounding electrode system should also be connected to the building steel and the slab rebar. This is because the building steel and rebar can serve as supplemental grounding electrodes, enhancing the overall grounding system. Building steel, if it's effectively grounded, can provide a very low impedance path to ground due to its extensive network and contact with the earth. Similarly, the rebar in the concrete slab, if properly connected, can also contribute to the grounding system's effectiveness. The connection to building steel should be made using approved methods such as exothermic welding or listed connectors. The connection to the rebar should also be made using appropriate connectors designed for that purpose. The NEC section 250.52 outlines what can be used as grounding electrodes, including metal frame of the building and concrete encased electrodes. Let's talk about the ground rod size. The NEC doesn't specify a minimum diameter for ground rods, but it does require that they be long enough to achieve a certain resistance to ground. A common size is a 3/4 inch diameter copper-clad steel ground rod, which is often considered sufficient. However, the effectiveness of a ground rod depends on the soil conditions. In areas with high soil resistivity, a single ground rod may not provide a sufficiently low resistance path to ground. In such cases, multiple ground rods may be required, spaced at least 6 feet apart, or the use of other types of grounding electrodes, such as ground plates or chemical electrodes, may be necessary. The NEC Section 250.53 provides requirements for the installation of ground rods and other electrodes. The resistance to ground of the grounding electrode system should be tested to ensure that it meets the requirements of the NEC, which typically specifies a maximum resistance of 25 ohms to ground. If the resistance exceeds this value, additional grounding electrodes must be installed until the required resistance is achieved. Moving on to the neutral jumper. The bare neutral jumper is used to bond the neutral conductor to the grounding electrode system at the service entrance. This bonding is essential for establishing a low impedance path for fault currents. The size of the neutral jumper is determined by the size of the service entrance conductors or the overcurrent protection device protecting the service. In this case, with an 800 amp opt, a 2/0 copper conductor would be required. This sizing is based on the NEC Table 250.102, which provides the minimum size requirements for grounding electrode conductors. It's crucial to ensure that the neutral jumper is properly sized and installed to provide a reliable bonding connection. Now, about oversizing the common ground. The NEC does not require oversizing the common ground. However, there are situations where it might be beneficial to do so. For example, in areas with high fault current potential or frequent lightning strikes, oversizing the grounding conductor can provide an extra margin of safety. A larger conductor will have a lower impedance, which can help to reduce the voltage rise during a fault and improve the performance of the grounding system. Additionally, oversizing the grounding conductor can help to reduce the risk of corrosion, as a larger conductor will have more surface area and be less susceptible to degradation. However, the decision to oversize the grounding conductor should be based on a careful assessment of the specific application and the potential risks involved. It's important to consult with a qualified electrical engineer to determine the appropriate size of the grounding conductor for a particular installation. In summary, the common grounding method used by the contractor is acceptable, provided that all the conditions are met. The 3/0 ground wire must be continuous and unbroken. Each panel must be connected to the ground wire by a lug bolted to the enclosure. The lug must be properly sized for the wire used, and the ground wire must be connected to the building steel and slabber bar. An additional ground rod or water pipe grounding is not required in this case, but it may be beneficial in certain situations. It's important to ensure that the grounding system is properly installed and maintained to provide a safe and reliable electrical system. Let's discuss the importance of proper connections in the grounding system. Each connection point in the grounding system, from the lug bolted to the panel enclosure to the connection to building steel and rebar, must be meticulously executed to ensure a low impedance path to ground. The use of appropriate connectors listed for grounding is paramount, as these connectors are designed to maintain a secure and corrosion-resistant connection over time. Regular inspection and maintenance of these connections are essential to identify and address any signs of corrosion or loosening which can compromise the effectiveness of the grounding system. Torque specifications for bolted connections should be strictly adhered to, and anti-oxidation compounds can be used to prevent corrosion, particularly in dissimilar metal connections. Another critical aspect is the proper bonding of metallic components within the electrical system. Bonding ensures that all metallic parts that are likely to become energized are connected to the grounding system, providing a common reference point and minimizing the potential for voltage differences that could pose a shock hazard. This includes metallic conduit, enclosures, and equipment frames. The NEC provides detailed requirements for bonding in Section 250.92 and 250.96, specifying the types of bonding jumpers and methods to be used. Furthermore, it's important to consider the impact of electromagnetic interference, or ME, on the grounding system. In sensitive electronic equipment, EMI can cause malfunctions or data corruption. A properly designed grounding system can help to mitigate EMI by providing a low impedance path for unwanted currents to flow to ground. This may involve the use of shielded cables, filters, and dedicated grounding conductors for sensitive equipment. The design and implementation of an effective grounding system requires a thorough understanding of electrical principles, the NEC, and best practices. It's essential to consult with qualified electrical professionals who have experience in grounding system design and installation to ensure that the system meets all applicable requirements and provides a safe and reliable electrical system. In addition to the physical components of the grounding system, it's also important to consider the administrative aspects of grounding. This includes maintaining accurate records of the grounding system design, installation, and maintenance. These records should include details of the grounding electrodes, grounding conductors, bonding connections, and test results. Regular inspections and testing of the grounding system should be performed to ensure that it continues to meet the requirements of the NEC and is functioning properly. The results of these inspections and tests should be documented, and any deficiencies should be promptly corrected. Furthermore, it's important to educate personnel who work on or near electrical equipment about the importance of grounding and the proper procedures for maintaining the grounding system. This education should include information about the hazards of improper grounding, the proper use of grounding equipment, and the procedures for reporting any grounding deficiencies. By implementing a comprehensive grounding program that includes both physical and administrative controls, organizations can ensure a safe and reliable electrical system for their employees and customers. The topics to always keep in mind are NEC compliance, qualified personnel, proper connections, bonding, EMI mitigation, documentation, regular inspections, and personnel education. Also remember the importance of grounding system testing. Grounding system testing is crucial to verify the effectiveness of the grounding system and ensure that it meets the requirements of the NEC. There are several types of tests that can be performed on a grounding system, including ground resistance testing, ground impedance testing, and continuity testing. Ground resistance testing measures the resistance between the grounding electrode system and the earth. This test is typically performed using a ground resistance meter, which injects a test current into the earth and measures the resulting voltage drop. The resistance is then calculated using Ohm's law. The NEC typically requires a maximum ground resistance of 25 ohms to ground, although some applications may require a low resistance. Ground impedance testing measures the impedance of the grounding path, which includes the grounding electrode system, the grounding conductors, and the bonding connections. This test is typically performed using a ground impedance meter, which injects a test current into the grounding path and measures the resulting voltage drop. The impedance is then calculated using Ohm's law. Ground impedance testing is particularly useful for identifying high resistance connections or other problems in the grounding path. Continuity testing verifies the continuity of the grounding conductors and bonding connections. This test is typically performed using a multimeter, which measures the resistance between 2 points on the grounding system. A low resistance reading indicates good continuity, while a high resistance reading indicates a problem with the grounding path. Regular grounding system testing should be performed to ensure that the grounding system continues to meet the requirements of the NEC and is functioning properly. The frequency of testing should be based on the specific application and the potential risks involved. In general, grounding systems should be tested at least annually and more frequently in areas with high fault current potential or frequent lightning strikes. The results of grounding system testing should be documented, and any deficiencies should be promptly corrected. Lastly, let's touch on the use of supplemental grounding electrodes. While the NEC allows for the use of a common grounding electrode system for multiple service entrances, it may be beneficial to install supplemental grounding electrodes at each service entrance. Supplemental grounding electrodes can help to reduce the overall ground resistance and improve the performance of the grounding system. They can also provide an additional path to ground in the event of a failure in the primary grounding electrode system. Supplemental grounding electrodes can be installed in a variety of configurations, including ground rods, ground plates, and chemical electrodes. The choice of electrode type and configuration will depend on the specific application and the soil conditions. It's important to ensure that supplemental grounding electrodes are properly installed and connected to the grounding system. They should be bonded to the primary grounding electrode system using grounding conductors that are sized according to the NEC requirements. The installation of supplemental grounding electrodes should be performed by qualified electrical professionals who have experience in grounding system design and installation. They can assess the specific application and the soil conditions to determine the appropriate type and configuration of supplemental grounding electrodes. By using supplemental grounding electrodes in conjunction with the common grounding electrode system, organizations can ensure a safe and reliable electrical system for their employees and customers.